This time I'm gonna do a lecture about binary trees, which I like this topic a lot. I remember being taught this in college, and I feel like maybe this is some of the experience that you might not get as a bootcamp student. Maybe I'm sure some bootcamps do cover this, but I'm gonna cover it. And I think I would say this is maybe one of the top two most important data structures in computer science. The other one is probably hash tables, but I think this is extremely important. It's trees are the underlying technology to databases, and also to just in general a lot of the code that we write. You might not even know it, but you're using trees underneath. I actually did make a video with Hui Qi about how databases work, where I get into trees a little bit in there as well. So there's two terms that people in the computer science circles throw around, and those are binary tree, but also sometimes they say binary search tree. So binary tree by itself is a more general term. Binary search tree is a little bit more specific. We'll talk about both of them. So a binary tree is anytime you organize. Oops, sorry. Actually, let's talk about binary tree in terms of the linked list. Okay, so with a linked list, so I'm gonna assume that you are familiar with the linked list, and linked lists are usually depicted this way. This little thing here with the two lines, that means null. That's a null pointer. So these pointers, each one of these pointers, that's the next pointer, right? That's saying, well, the current value is 1, and the next value is whatever that node has inside it. And a binary tree is actually an extension of the linked list. What you do is just add one more arrow here, and that becomes the binary tree. So each node has 2 arrows now instead of potentially 2 arrows. Each of the arrows can still be a null pointer, in which case it looks like this, or you just don't draw it. No, you don't have to draw these null pointers if you don't feel like it. So this 5 would mean it has nulls for its children. Or we could do something like this. So this is a binary tree now. And instead of calling the pointers next, we'll call them left and right. Let's let this one be left, and this one be right, and so forth. Usually you would draw it in a top-down fashion, like this. Okay, so this is a tree, and if you had a tree like this, you could write a algorithm to traverse it. And like if I had something organized in this way, I wanted you to print out every number inside this tree. How would you do it? So I'll call this function print, let's say. I want to print, let's say I want to print this whole tree like that, right? So how would you do it? You would probably use recursion. You would say, well, I want to, in order to print this entire tree, first I want where this entire tree is represented by the root node, the one node, you would say, well, I have a node, so this guy is the node. I would print my left child, and then I would print my right child, and also I would print myself, maybe like console.log my own value, like that. And that's mainly what that's what you need to do, except for the edge cases, which are the null pointers. So you probably need to check if node is null or not once you get here, but that's the basic idea. So you would end up doing, basically, you want to print the whole tree, then you end up calling p on this subtree, and then they would end up calling p on just this 4, and you end up calling p on just this 5. And then when all of this is done, you end up calling p on 3, right? And you can do this in different orders, as in you can order these 3 statements any different ways. Like you could do this console.log my value first, or you can console.log the left value first, or not console.log, you can print the left subtree first, or you can print the right subtree first. These can be ordered different ways, and you probably might have read in the literature that there's 3 orders. There's the in order traversal, pre-order traversal, and post-order traversal. Pre-order traversal means you print yourself first. So you print node.value. You print the 1 first before you go down to the left subtree and right subtree, and then you do the left and then you do the right. Post order means you do the left and then right, and then you do yourself. And in order means you first do the left and then you print yourself, and then you do the right. And the reason it's called in order is because it's like if you were going in order from the left all the way to the right, as it is depicted in this diagram. So if you do in order, you would end up doing 4, 2, 5, 1, 3. You're doing this comb from the left, visually from the left to the right. Does that make sense? And let's do like an example of the in, the pre, and the post. So 1, 2, 3, 4. 5, 6. Okay, so if we did a in order, it would be like, well, I want to go into my left subtree first, and then I keep going left first. So you end up printing 4. And then for the 2 node, after it does the left subtree, it would print itself. So then it would print 2, and then it would go back up to the 1 node. Oops. And then go back to the 1 node, and then 1 node will print itself, and then go into the right subtree. And the 3 node will say, I want to do left first. And then it come back up and it does 3. And then it goes to the right child and does 6. So this is in order traversal.
Hey, Toby,
yeah.
If the 2 had a 1 had a right node?
if this guy had this one here.
Yeah.
Okay.
Would that have printed between 2 and 1?
Yes, it would have. It would have done the function call for 2 would have said, I want to traverse to my left side first, and then print myself, and then I want to traverse my right side. So let's include that. I'll stick this 7 in here. Okay, so this in order, but it's visually it's exactly like you're doing you're going from left to right visually as it's laid out on this diagram. That's what in order traversal gives you. Let's do pre-order traversal. Pre-order traversal is like I am pre, meaning the current node it goes before the children. So that means when I traverse the one node, I'm printing myself first before I go into my children, and then I'm gonna go left child. So then I'm at node 2, and node 2 says I'm printing myself first, and then I'll go into my children, and I'm gonna go left first, and that's gonna print 4. Now it comes back to the 2 node, and 2 node says I'm going right child. It prints 7, and now I'm done with 2 node. Goes back up to 1. 1 has already printed itself and its left child, so now it's going into the right child. The 3 node says I'm printing myself first, and then goes into the left child 5, comes back up to 3, and then we're going down to the right child 6. So that's pre-order traversal. Any questions there? Okay, I will do post order means I am post. I come last after my children have gone. So post order does I'm on the 1 node, I go to 2 first. But 2 doesn't print itself either. It wants to deal with the children first. So 2 goes down to the left child, and then 4. 4 doesn't have any children, so it's already done with that. So it just prints itself. And then it comes back to 2. And 2 says, okay, I'm done with my left child, but I'm going to do my right child first before I print myself. So it prints 7. And then finally 2 will print itself. And then now we're done with 2. Comes back to 1. 1 says, I'm done with my left child. I still have to do my right child first. So go down to 3. 3 goes to 5 first. And then 3 does its other child, which is 6. And then finally 3 prints itself. And then 3 finally brings it back to 1. And 1 prints itself. So this is post-order traversal. In my opinion, the only one that is reuseful or is commonly used is in-order traversal, because of course you can do in-order traversal in reverse too. Like you can go right first and then left. Like in all 3 of these, we've done left first and then right. So like the reason in-order traversal, in my opinion, is the most useful one is because it's directly tied to how the binary search tree works, which I'm going to go into now. So any question about this so far? So far I haven't introduced this sort of search element to this. So far I've been talking about the generic binary tree. Okay. So now given this, binary trees like this, without the search element, is actually not super useful. So let's talk about the binary search tree, sometimes referred to as the BST. So BST is a binary tree which maintains a constraint on there's this rule that has always to be satisfied in order for a binary tree to properly be a binary search tree, and that rule is for any node for any node in the tree, the value of the left child is less than the node value, that node's value, and that node's value, and that node's value is less than the value of its right child. Okay, so to visualize that means so this tree satisfies this constraint, while this one does not. Okay, so basically, if you do the in order traversal, if you go traverse all the nodes from left to right, the values must go in increasing order, strictly non-decreasing order. That's what this rule means. And if this rule is satisfied by your tree, I'm gonna write a X mark here. So if this rule is satisfied by your tree, all of the nodes of your tree, then it is a valid binary search tree. If it does not, then it's not a valid binary search tree. And the algorithms that deal with the binary search tree will assume that it is already a valid binary tree, and the algorithms that make modifications to a binary search tree will ensure that after the modification, this condition is still preserved. Otherwise, things are going to break. Okay. And I kind of want to give an intuition about why this is valuable. Probably let me show you how you would go about searching something in a binary search tree. Well, actually, no. I want to talk about arrays and linked lists first. Okay. Yeah. So I want to ask you guys a question. What are arrays good at, and what are linked lists good at?
I would say arrays are good at index lookup, and linked lists are good at basically insertion and removal.
Yes. Yeah.
Both of them approach O1 in those cases.
Yes. So linked lists are like big O of 1 for insert and removal. Only if you insert at the beginning and remove at the beginning, right? Whereas arrays is big O of 1 for random access, accessing any index. Both of them are pretty bad at what if you wanted the data to be sorted, right? You want to be able to access the data in a sorted way, as in you want it to be you would like to, like, if you have a name that you want to look up, you want to find the node that contains that name. And your list, or either your linked list or your array is like contains a database of a bunch of people or something, and you want to do a lookup on the name of the person, right? So if you want to keep them sorted, if you assume that the linked list is sorted and the array is sorted, then to what would be the big O for finding the person in that sorted structure for linked list versus array? Finding a person. Anyone?
Isn't it ON in both cases?
In a sorted LL versus a sorted array, is it big O of n in both cases?
Yeah, it makes no difference that it's sorted.
What any other opinions?
I think it would be log n for the linked list, because you can go half and then half and then half, right? So when you're going through the sorted linked list.
You talk about the binary search.
The binary. Yes.
Yes.
Sorry, I may have missed the question too, but.
Like if you have a linked list that is sorted, that like you're told that this is linked list is sorted. Why is my pen laggy? And who knows how many things is in there?
I guess you don't know, right?
You don't know. Versus you store the same, and I'm doing numbers, but these could very well be not numbers. It could be people with a bunch of fields in each person.
But are we assuming that the array is sorted too?
We are also assuming the array is sorted. And I'm saying, I wanna find the person number 97 in this linked list or in this sorted array. How much time relative to the size of the thing would it take?
So is the array not log because to find it?
Yes.
Okay, it is log because it's half, and then you search the first half, and then because it's ordered. So if it's, let's say 500 is the middle one, it's in the first half. Then you look at 250. Then you look at 125.
Yeah, exactly. Yeah, exactly. So for the array, you can do big O of log n. You can do big O of log n via the binary search. Can you do that with the linked list?
No, it makes no difference. There are no shortcuts. If it's the last item, even if you know it's the last item, you still have to traverse every item.
Yeah, so
it's ON.
Unfortunately for the linked list, you cannot use this binary search trick. But for the array, you can, because random access is a big O of 1. So you can access anything within the array with the same amount of time. So that's like an advantage for arrays. However, what if I wanted to insert to this sorted array versus if I wanted to insert into this sorted linked list? So insert a new person or a new number into this sorted structure. What would it look like for the sorted linked list, and what would it look like for the sorted array?
I think in both cases it's ON.
I think it would be the same, wouldn't it?
You mean in both cases it is the same? But what is the big O? Johnny said it's big O of n. Do you agree?
I think it's big O of n for linked list again, and big O of log n for array again, because you would use binary search to figure out where the insertion should go.
Yes, but
That's true, but then you have to actually physically move everything, and if it happens to be the last insertion one, then you're gonna have to shift everything over. Worst case scenario.
Yeah, that's the rub. Is with the array you have to make room to insert that element, which is really nasty actually, because like copying a lot of things in memory, it's expensive. So, so the array case is actually ends up worse than the linked list case, because the linked list, once you find where you need to insert, you just move a couple of pointers and you're done. But in either case though, they're both big O of n, because like you find a place that like in the middle, you don't know where. It could be here, it could be here, but if you don't know, then on average it's half of the size of the array, right? So half is, that's a constant factor of versus n, so it's still n. So you're moving about like on average half of the elements over by one in order to insert the new thing. And for and then searching is the same. You're on average you're searching half of the list or half of the array. So basically, like this is a case where both the linked list and the array are not doing that great. If what you want is to keep the data sorted in some way, and that is the problem that the binary search tree solves. Specifically, a binary search tree is able to keep your data sorted in a way such that both finding a thing in the structure and inserting a thing into the structure, both of those give you a big O of log n. And intuitively, the way you can think about it is kind of, well, if the array is sorted and you can look through it via a binary search, like maybe the array is 1, 3, 4, 5, 6, 7, 10, 12. Okay. You can actually, if you inserted all these numbers into a binary tree, well, that might look like this. A binary search tree. So this might be like 7 maybe. Oh, okay. 10, and then 10 might have a 12 here. Okay, so a binary search tree containing a bunch of sorted numbers would look like this. And you can please verify that this is a valid binary search tree based on the constraint, right? Because of the constraint, we now have this condition that if we do an in-order traversal, we'll get the numbers printing in order of increasing, non-decreasing order, right? And if you think about if it was an array, what you're able to do to search a number in log n time is this binary search trick, which is basically you cut it in half, look at the middle element, and then you start at that middle, and then on the other side you cut that in half again. Well, if you're traversing a binary search tree, you're actually doing the same thing. Like 5 is the half, is the middle of the array, right? So just by traversing this tree in this manner, you are basically performing the binary tree. So therefore, if you want to search for a number in this binary search tree, the algorithm would be, hey, I want to find, let's say I want to find 6. I want to find 6 inside this tree. Okay, so I'm going to compare the target, which is 6, to my current node, right? Initially, I'm going to say find 6 in this tree. And if 6 is greater than the value of the current node, I know that it cannot possibly be in the left subtree. It must be in the right subtree if it exists, right? So there's actually no need to inspect the left subtree at all. So what I would do is just recursively call the find function only on the right subtree. So to say find 6 in the right subtree now. And then
to clarify, just to make sure I didn't miss anything, we have not talked about how this tree got established, right?
Correct.
Okay.
I will need to talk about that, but
yeah, that's no problem. I just want to make sure I didn't miss anything.
Yeah. There's the searching and there's the insertion. But we're assuming, you know, somebody has put this tree together in the correct way for now. So now we're gonna say, yeah, we're going right. We're not going left. We're going right. And now it's gonna say, okay, I'm looking at the value 7 right now. I'm gonna compare it with my target, which is 6, because 6 is less than 7. Therefore, it must be somewhere on the left subtree of 7, if it exists. So then you're gonna do, I'm gonna find 6 again within this 6 subtree. And then when you see that 6 is the same value as the target, you say, yeah, we found 6, and that's where it is. And the number of recursive calls we had to do in order to find 6 is the maximum it can be, is the height of the tree, is the maximum height of the tree. And the height of the tree, wouldn't you know it, is log of n. So this is the height of the tree, and the height of the tree is log of n, where n is the number of elements in the tree. So that's kind of trick number 1. And if you think about it, this is exactly what the binary search would have done. By doing this selective tree traversal, where we are at each node, where we are sure about the path we're going to take to traverse down the tree, we're only going to traverse one path of the tree. Like we went this way. If we were looking for 12, we would have went this way. If we were looking for 4, we would have went this way. And in every case, the number of nodes we traverse is the height of the tree. And yeah, the binary search tree, the binary search algorithm on the array would have done the same thing. Basically, it would have done like 5, and then we're gonna break it in half and like look at 3, and then 4 is greater than 3, so I have go to 4, right? So this is trick number 1, is the look for a specific thing in the binary search tree, which is a sorted structure by its definition, by that constraint rule that we defined, is always going to be log of n. Let's talk about insertion now. So insert for a binary search tree. Okay. So let's do another tree. Okay, we're gonna insert a new item into this tree. Let's say I want to insert the number 2 into this tree. The first step is to find the place where you're going to insert it. And that's actually identical to the algorithm for finding an element in the tree. You would say, oh, well, my target is 2. I would like to insert a 2 into this tree. Well, if I'm looking at 5, I know it has got to go somewhere on the left of 5. So then we're looking at 3. And then because 2 is less than 3, we know it has to go somewhere to the left of 3. And then now we're looking at this 1. And that's where we're looking at 1, and then we're saying, oh, that's less than 2. So 2 has to go to the right of 1. Because 2 is greater than 1. And we found a home for this 2 now, right? And the reason we know to just insert this here is because 1's right child is null. So that's like an open slot that you can put things in. So 2 becomes a right child of 1. So we'll do another one. So let's say 2 is here now, and let's insert another number. We'll insert a 8. Okay, so 8 is greater than 5, so we're gonna go right, and then 8 is greater than 7. We're gonna go right again. 8 is less than 9, so 8 is gonna become the left child of 9. Okay, and again, the big O for this insertion algorithm is the height of the tree. It's the log of n, because it's equivalent to like doing a search for the element, for the place you're going to insert the thing, and then the inserting of the thing is big O of 1. So the bigger, it's just log of n, basically. And that is kind of that's the secret ingredient that makes this binary search tree fast in both cases. And traversal of the tree is still gonna be big O of n, because you still have to go through all the elements of the tree. There's no way around that. But the insert and searching and delete, for that matter, all of those things are gonna be big O of log n. I should write a big O here. And yeah, that's why this guy is useful here. Any questions at this point?
Are you going to do an example where there isn't, like, can the tree be in such a way where there's a gap? So you need to, like, is insertion always as nice as there will be a slot for it?
Oh, what would be a case that where it doesn't have a slot? You're saying we need to insert in the middle of the tree? That actually doesn't happen, but
yeah,
because you would always just always get to the bottom of the tree, like if you
left or right.
Yeah, if you go like 5.5, let's say 5.5, then it'll be like 5 go 7 go 6, and then here 5.5.
And I imagine duplicate values, you go to where you think it would be, and if it already exists, you do nothing.
No, if it already exists, you actually do just, it's possible to have duplicate value. Like I want to insert 4 into the tree, So that 4, go left here, go right here, and then 4 will just be a child of 4. So you can do 4 here.
Wouldn't it be valid to do nothing though?
Oh yeah, if you want the keys to be unique, which that's a great point. Because binary trees are one of the ways in which you can implement a map, and by map I mean a map is kind of how JavaScript objects are implemented. I know like ECMAScript has the map, the proper map, like where you have to say new map. But
this is what you're talking about is the like the JavaScript map.
Yeah, the JavaScript map in C#, it's dictionary, right? Dictionary. So, or in Ruby is hash. There's many names, but basically it's a thing where there's a key and a value, and the keys are unique, right? In a map, and so JavaScript object literals, JavaScript map, or dictionaries. In other languages, they call them hash. All of these things are basically you have a key, and given a key where keys are unique, you can store any value that you choose under that key. You can override the value based on this, but you actually cannot have duplicate keys where we are going to interpret these values as the key here. So if you're using it for that application, then you should not have duplicate values of the tree. You would just, when you're trying to, instead of saying insert, you'll probably call that set. I'm going to set 4 to like Harper or something. And then you would go down the tree and find the for node, and then inside the for node that there's an additional value field inside the node that's storing this value, and you're changing it to Harper. Okay.
Yeah, that makes sense.
Yep. So yeah, I think it's really important to associate this data structure with like the stuff you use, and the stuff that you use may or may not use this tree data structure. It could also have used a hash table to implement this. It depends on the implementation detail. Like some programming languages choose to use a tree to implement a dictionary, others choose to use a hash table, and there are different trade-offs.
Can you talk about those briefly?
Yeah. Good question. I probably should do a talk on hash tables, but I'll talk about it briefly. So hash tables is basically an array, and under each, like you in both, like, so first of all I want to ask you, like, does it make sense like that you can use a binary tree to implement a dictionary? Is that vague for anyone? Huh? Yes.
That's very concrete to me. Yeah.
Okay, good. And if any one of you have a question about that, I'll try to clarify right now.
I'm thinking, it makes a lot of sense when the keys are numbers, but how does that translate exactly if the keys are not numbers?
So yeah, everything I've been doing thus far with the reason I use numbers is because they're very short to write on a slide, but they don't actually have to be numbers at all. So like if I say they could be strings, right? John, if I put John into a binary tree and I wanted to insert Toby, well, Toby is greater than John in the alphabetic sense, so Toby should go to the right. And then if I want to put Jason into the tree, I was like, Jason goes before John, so it should go to the right of John, and so forth. So actually, there's nothing about it that requires these values be numbers. All that's required is that there's a way to compare the keys, and you're able, like, you need the comparator function defined for this data type that tells you whether one is less than the other or greater than the other or equal to, and that's it.
Okay, that makes sense. So, and I don't know if this is too much, we don't have to get into this, but like what this then leads to is like the keys are in some kind of guaranteed order. So, I actually don't know offhand, like if the JavaScript map, if you print a map out, is it going to always show the keys in the same order?
In there, the spec doesn't actually tell you how it needs to be implemented, and the spec, I think, specifically avoids saying that the order needs to be guaranteed, and therefore the order is not guaranteed.
I guess I would just think that that's it. If this is what they use under the hood, that should be easy, shouldn't it? Because it's like a straight left to right traversal.
Correct. But the spec doesn't require it to be ordered, basically, and I think the reason is they might implement it as a hash table.
Right. We don't know what they use. Okay.
So in the case of a hash table, actually, and that's one of the differences. A hash table is not ordered in it. There's not a way to. So let's talk just briefly about hash tables. So hash table would be like you have an array, which each element of the array, initially all the elements of the array are empty if you have an empty object or an empty dictionary. When you insert stuff to it, like let's say you want to do set, maybe I'll use this index notation. Let's say I'll call this D for dictionary, and I want to set name to John. So how does a hash table do this? We talked about how a binary tree does this. A hash table hashes the key value, and by hashing I mean converts it into a number, an index number that is an index for this array, actually. So that hash function is called, I'll call it H. So if you hash the key, in this case name, it will give you a index number for this array. Maybe it gives you a 4 here. And then now you know, after having hashed the key, where this information should go within the array. So you go and stick John in here. And a guarantee that you must have for hash functions is that for any input, it should always give you the same output. Otherwise, this scheme is not going to work, obviously. Well, I don't know if using name was a good idea here for this example, but I guess I was thinking like name and age, but maybe we, instead of doing that,
and why did that get inserted into the middle of the structure?
It's kind of random. I'm gonna, instead of doing that, I'm gonna change my example. I'm gonna say the key is the name of the person or the name of the object. I'm gonna say, and the value is, I don't know, some random number I'm gonna put in here. So I'm gonna hash John. And your question about like why is this a number? Why did it go into the middle of the array? It's kind of random, or not random like random number generator random, but the hash function is something that conceptually there's no way to predict, given what the key is, what it's going to output, what number it's going to output. So like it could go anywhere into the array. You don't know unless you know the implementation of the hash function. So if we do hash Rachel, and depending on the implementation of the hash function, it may give you like, I don't know, it'll give you 7. So I put 4 here, so 4, 5, 6, 7, and let's say we put a 10 here. I think I'm confusing matters by using 4 twice, but this is 4, 5, 6, 7, 8, 3, 2, 1, 0. So, but basically, this is how the hash table stores things, and so you might imagine if you do more of these, you fill in more people's names with numbers. Each person's name is attached to some number in this way. You might get this filled up. Maybe like Jason is here, Toby is here, and then Colin is here. You just get more people filling this up, right? And then you're gonna try to add one more person. It's not gonna work, right? So this hash table can get filled up, and actually it doesn't even have to get all the way filled up before a problem occurs, because this hash function could give you the same index number for different key values. So it potentially could happen that if you hash the key JSON, it gives you a 4 as well as the value. Like you could have multiple keys give you the same array index, and that you have a collision. That's called a collision. So if you have a collision, like I need to store both Jason and John under the index 4. And what is usually done is you actually make this a little linked list structure. And maybe Jason has the value of 8. So, and then you also have to remember which one of these values go with which actual key. So you have to remember, 4 is for John, and 8 is for Jason. And then now it's starting to look a little weird, because, well, what if this linked list gets like really, really long? Well, obviously, ideally, that is really bad. So if we want the thing to be performant, this linked list getting long is not going to help our search times. The whole point of using this scheme is that this h function, we're going to implement it in a constant time way. So this guy should be big O of 1. So then that gives us the ability to access a thing with a big O of 1 all the time, just like a normal array. But if you're going to have collisions and we have to store multiple things under one index, that's going to hurt that efficiency. So what's usually done when there's some code that manages the hash table, and when it sees that, oh my god, this is getting really full, and we're having a lot of collisions, and we have these linked lists that we have to manage now, and it's hurting the efficiency. Usually what it does is it allocates more memory and constructs a larger array than this one. So it's like, I need a much larger array so that I won't have as many collisions, or any at all, ideally. And then it redoes everything. It like has to redo this hash function and has to move everything over to this new array. and it might be different positions now because it's going to do a modulus operation based on the size of this new array. And yeah.
I know we're running out of time, but I have a question.
Yeah.
This makes sense to me. Well, I guess how are lookups and insertions actually performed in a efficient way? Because you have the indexes of the array storing the values, but how do you then know if someone wants to look up John, what index to find in the array?
Oh yeah, forgot about that. Sorry.
Insertion and deletion.
Yeah. It's the same actually. You just, if someone wants to access the key John, then you do the hash function on John again, which I haven't talked at all about what hash functions are. But
I know that part, but how does for help you find the index in the array? It seems like you'd have to iterate the array.
Oh, sorry. I just I did not make that clear. 4 is the index of the array. I messed it up by making both the index of the array and the value 4. So let's say I wanted to set John to 5, and then 5 should go here. But the 4 is the index of the array.
Okay. That brings up another question to me, because I know in C# hash codes are ints.
Yeah.
Doesn't that mean that you need an array of size 2 billion?
No, I mean, you would just do a modulus on the size of the array at some point.
Okay, and so that's how they determine basically
how
many buckets there would be.
Mm-hmm.
Okay, that makes sense.
Yep.
That's great.
So you probably actually modulus the size of this array, which that's not exposed to you because that's an implementation detail. So if now let's try, we don't have a lot of time left, so I'll just try compare, like if we implemented the dictionary using binary trees versus hash table. Versus binary search trees, I should say. Let's wish the search, if we want to search something, search for a key, versus we want to insert something by a key. There are more, but let's only do these two. What is the big O of searching for a key with a hash table? We already talked about the binary search tree. They were big O of log n in both cases.
It's O1, right?
Yes. You're talking about this one here.
Yeah.
Yes. What about insert?
Also O1.
Also O1.
Well, I mean, it's technically, I guess, a lot more, but it's approaching O1. Is the idea.
It's actually right. It depends on whether the hash table is like quote unquote healthy, right? or like if the hash table, like you go to that index and it's got a huge linked list that you have to traverse, then it's, well, is that really O1? And also, what if you're like accessing that thing and then the hash table engine decides, actually this is too full, I'm gonna do a maintenance task and expand my array and then copy everything over. That's actually very expensive. But the point of the hash table is you amortize the cost of that over a long period of time, so that if you average it out, it's more or less big O of 1. That's the point. if you're like accessing the hash table like millions of times, and that those maintenance tasks only happen on a very, very small percentage of it, then over a long period of time, it's more or less big of one.
On access, like read never suffers from that. Only insert. In fact, delete really doesn't suffer from it either, unless you're clearing out.
Yeah.
Something. So it's really only insert that potentially suffers.
Yeah. I'll do like sometimes on insert. Sometimes you have maintenance tasks that you might have to do. We actually haven't talked about the maintenance tasks associated with binary trees. It does happen. It does exist as well. But I'm kind of running out of time. So like, to give you an example, to just explain why maintenance for binary trees is necessary, might be necessary, is what if you have like, what if you you start with a tree that has a 3 in it, and then you're like, I want to insert a 4. And then you're like, let me insert a 5. Let me insert a 6. Let me insert a 7. Let me insert an 8. I'm just following the standard insertion algorithm for binary search tree, right? Go to the right if it's greater, right?
But it's a linked list.
You're not taking advantage of the binary search tree. You're not using the left child on any of the nodes if you're inserting in order like this. So for that reason, there are some implementations of binary search trees that have these automatic maintenance component to it that always guarantees, as you're inserting stuff into it, always guarantees the tree is more or less balanced. And those are red-black trees is one. Another one is called weighted balance tree, I believe. Yes, and if you're interested in that, check out my database video as well. I do talk about that a little bit. Yeah, and I think that's good. I think that's a good place to wrap up. And next time we'll do some code challenges. How about that?
Cool. Toby, I'll call you in a minute.
Okay.
The rest before our time.
Alrighty. All right, thanks everyone.
Thanks, Toby.
Thanks, guys.